Welcome back to another video lecture for section 4.1. This starts unit 5, and this is the second to last unit in college algebra. So we begin unit 5 by looking at inverse functions, and then we're going to do lots of things throughout unit 5, inverses, etc., which just kind of help you do the last few kind of not so straightforward solution techniques that we have in college algebra. So up until now we've dealt with relatively simple objects. We've dealt with linears, we've dealt with quadratics, we've dealt with polynomial objects, and the kind of long and short of it is that the linear is super basic, it's easy to solve. A quadratic, we can do one of about 3 or 4 different techniques to turn it into a linear, which we can then solve using linear techniques. In polynomials, we can do synthetic division and use the rational root theorem and Descartes' rule of signs to kind of figure out where the zeros are, and then we can get it into a quadratic, which we can then use one of 3 or 4 techniques to turn into a linear, and we can use linear techniques to solve. So what we've been doing with linear techniques the entire time is we've actually been figuring out what the input was that resulted in a specific output. And that kind of idea is exactly where we'd like to start with our discussion for inverses. So on inverses, what we need to recall first is that a function is just a rule or a set of instructions that maps an input value onto an output value. So they can look like a set of ordered pairs. For example, here I have a function that takes 1 and sends it to 3, it takes 2 and sends it to 4, and it takes 3 and it sends it to 5, where all of the x coordinates of this function are input values and all of the y coordinates are output values. And what I'm going to do real quick is I'm going to kind of circle the input values in this green color. And so something happens to that green circled value that sends it to the y coordinate in the ordered pair. So that one's something pretty simple. It's like just add 2 to the inputs. It's like x plus 2 would be our function there. And what we are aiming to do with an inverse is, let's say that I knew that the output value was something like 5. Well, then I could say that x plus 2 is equal to 5, and of course we have nice easy like algebra 1 techniques to find out what the input was that produced that output. And that's the idea behind an inverse function. It just is a rule that undoes everything that our function did. And another way to say that is that if we know what the output is, we can plug it into the inverse function to figure out what the input that produced it was. So in x plus 2, of course, 1 produces 3, 2 produces 4, 3 produces 5. If I take 5 and I put it into the inverse, it should give me 3. 4 into the inverse should give me 2, and 3 into the inverse should give me 1. And I've summarized that right here, where I have f inverse 3 goes to 1, 4 goes to 2, 5 goes to 3. And so what you may want to notice here is that these kind of green circled input values in the inverse function became these green circled output values. The inputs become the outputs, and the outputs become the inputs. What that represents is that the domain and the range just flip-flop. So whatever the domain for one of these was, it becomes the range of the inverse function, and whatever the range of the inverse function was becomes the domain of the inverse function. I think I said that wrong. Whatever the range of the original function was becomes the domain of the inverse function. Excuse me if I said that incorrectly. Okay, now a couple of quick notes. If we have some ordered pair x, y that's in our function f, then the flip-flopped version of that, y comma x, will be on the inverse function if the function has an inverse. Now, an inverse simply undoes everything that a function did. And kind of a last note here, you'll notice that I said that the range of the original function became the domain of the inverse function. Well, you've seen several functions back in like unit 3 or unit 2 even, where the range was not negative infinity to positive infinity, it was constrained somehow. So we kind of have to have a special like test to figure out If our domain is not equal to the range, well, then we may have some problems producing an inverse. We may lose some information, and we're going to cover that as we get further into this unit. But right now I just want to focus on kind of a common sense way to produce an inverse, and then we're going to talk about what happens when we get functions that are, well, not so common sense. So here, excuse me, here I have two examples. In example 1, I have the function 4x plus 1, and if we want to produce an inverse for this thing, let's just start asking ourselves common sense questions and see if we can't come up with what the answer has to be. If I were to plug 0 into this, well, then I get 1. If I were to plug the number 1 into this, then I get 5. If I plug 2 in, well, then I get 9. So I have 1, 5, and 9 as my outputs, and my inputs were 0, 1, and 2. You can kind of think of a number of different things that you might be able to do to those output values to send them back, but each time, think about how we were producing that output value. First, I would pick an input value that I wanted to know the output of, so I'm like picking a number, and I plug it in for x. Then I would multiply it by 4, and then I would add 1 to it. And in this case, where we have kind of a nice, easy single variable, we can just figure out, well, how do I undo that? Well, the last thing that I did in the original function needs to be the first thing that I undo in the inverse function. So if the last thing I did was I added 1, then the first thing I need to do in the inverse function is I need to subtract 1. The inverse operation corresponds to the inverse function. Well, then what I can do is I can cover up the part that I just undid. First, I picked a number, then I multiplied by 4. The last thing that I did there was multiply by 4, so the first thing I have to do now is divide by 4. So whenever I've already got something written down for the inverse function, I'm going to do a new operation. I have to make sure that I do it to everything that's in the inverse function. So I'm not just dividing x by 4, I'm dividing everything by 4. So I have x minus 1 all divided by 4 is apparently my inverse function. And we can double check that. If you remember, when I plugged in 0 here, I should have gotten 1 out. So what that means is when I plug 1 in here, I should get 0 out. Well, 1 minus 1 is 0, and 0 divided by anything is 0. That may be not so convincing because we had a 0 there, and obviously that's pretty easy to produce, so let's try a couple more. When I plugged 1 into the original function, I got 5 out. Now that's a pretty specific number. It doesn't seem as generic as 0, so maybe this one's going to be harder to produce. When I plug 5 in, I'm supposed to get 1 out of the inverse. So if you plug 5 in here, 5 minus 1 is 4, and then 4 over 4 is, well, just 1. So we can see that our inverse clearly works. One more for good measure. When I plug 2 into the original function, that was 2 times 4, which is 8, plus 1, which is 9. So that means on the inverse function, when I plug 9 in, I should get 2 out. 9 minus 1 gives us 8, and then 8 divided by 4 will, of course, give us 2. So you can see pretty easy that the inverse that we came up with does what we claim that it is supposed to do. Okay, and we can even do this with really complicated functions as long as there's like one x variable in our original expression for f of x. It's going to be super, super easy to come up with the inverse. And this is where that completing the square technique that we talked about in the polynomial unit and the quadratic unit is really going to come in handy if you have paid attention and learned that. But like I said, if you didn't learn completing the square, in all reality, if algebra is the terminal point for you, the only place that it might be useful to kind of recall how to do that is this stuff right here, because it's just not going to pop up very often in business or in any of your other majors, unless of course you're going to take higher level mathematics, in which case absolutely learn it. So here I've got a second example. F of x does something kind of funny here. I'm not going to play with the ordered pairs on this one because it may do something kind of weird. So for example, let's take, I'll just play with one ordered pair. I want to find one that works real quick though. Let's take x to be, let me find one that works. See if I can find one that's a whole number. I should have done this beforehand, but when I wrote the example down, I didn't think about it, so I apologize. If we let x equal to 5/3, because I know that one will work. If we let x equal to 5/3 here, let's see what the output value is before we figure out what the inverse function is. 3 times 5/3 is going to be 5. 5 minus 1 is 4. Square root of 4 is 2. 2 over 2 is 1, and 1 plus 1 is 2. And the reason I chose that specific number was because I didn't want to get some crazy weird like square root term here. It still works with the square root terms, but I wanted a nice easy integer number that we could play with. So what we need to do is we need to find a inverse function where when I plug in the number 2, I'm supposed to get 5/3 out of it. So plug in 2, I should get 5/3. Let's see if we can do that with our kind of common sense procedure. Well, first what we do here is we pick a number. I picked 5/3, then we multiply it by 3, then we subtract 1, then we square root it, then we divide by 2, and then we add 1. So what was the last thing that I did in that sequence of events? The last thing I did was add 1, so the first thing I have to undo is subtracting 1. Okay, cover it up. First I plug in a number, multiply by 3, subtract by 1, square root it, divide by 2. Last thing I did there was divide by 2. I have to multiply by 2 to undo that, so I put the 2 out in front, because remember you have to do it to the entire inverse function. First plug in a number, then multiply by 3, then minus 1, then square root it. So what I need to do is square this entire thing. I'm going to go ahead and clean it up a little bit just to make sure that we have it in a nice, easy to see format. Notice that I had to square everything, so even the 2 out in front of it got squared. Okay. So now I've covered up the 1, I've covered up the 2, I've covered up the square root symbol. First I plugged in a number, then I multiplied by 3, then I subtracted 1. So the last thing I did was subtract 1, now I've got to add 1. Okay, first I plug in a number, then I multiply by 3. Last thing I got to do, divide by 3. Okay, so what we need to do now is we need to double check to make sure that when I plug 2 into this, I do in fact get 5/3. And if that works, I'm put a big green check next to it, and we found our inverse function. And notice that all I'm doing to find these inverse functions is I'm asking common sense questions and undoing the very last thing that I did. Okay, so taking 2, plug in 2, minus 1, that's 1. 1 squared is 1 times 1, which is just 1. 1 times 4 is 4. 4 plus 1 is 5. 5 divided by 3 is 5/3. This thing works. Okay. So the long and the short of it is when you see examples like this, you can find a function that could potentially be the inverse for that function simply by following this procedure. What is the last thing I did? That's the first thing I'm going to undo, and then make sure you do that to the entirety of everything you've written down for the inverse so far. I'm going to show you what happens when we have more than one x. This can be a little bit more difficult to mess with, but I'm going to show you a way that we can produce something that acts like the inverse, and then we're going to talk about the subtleties of when a function actually does have an inverse and when it doesn't. I'm going to show you that with an example. Give me just a second, I'll clean up the board, I'll be right back. Okay, I'm back. I put another example up here. Now here you'll see a function that we've talked about many, many times in the example videos. I've got x squared plus 5x plus 6. Now in this thing, what I'd like to do is I'd like to find an inverse for it, or let's clarify this. I'd like to find a function that acts like an inverse for part of the expression. Then I'm going to show you what this thing actually looks like, and I'm going to show you graphically what the inverse is doing, and then we'll talk about what happens when we have a range that's a little bit different. I do challenge you to pause the video here and just state what the domain and range of this thing is. Maybe use a calculator to do that before you start watching the video again. I may include a question about that particular thing at the end of this video. Okay, so you paused it, you tried it. Here I have 2 x variables. So when I try to follow my common sense procedure, it's not going to work, because I'm going to say first I pick a number, then I plug it in. Well, what's the next thing that I do? Do I square it? Do I multiply by 5? Does it matter? How do we worry about order of precedence? What if they had different exponents? What do I do? Well, what I need to do in this case is I need some kind of procedure that will guarantee me that I can get my inverse. Now, we could do something kind of funny with this. We could attempt to complete the square here. And if I complete the square with this thing, then I'm going to have a function of one variable, and I'm going to be able to do my common sense procedure with it. But you have to remember how to complete the square in the first place. And I'll talk about how to do that. I'll show that as a second part of this as soon as I'm done showing you the general procedure. So the general procedure, if you don't know how to complete the square, we're going to replace f of x with y. The next thing we're going to do is we are going to switch the location of x and y. And what I mean by that is everywhere that I see a y, I'm going to write down x. And everywhere that I see an x, I'm going to write down y. And then what we have to do is come up with a way to get y by itself. So what we're going to do is we just swap where the x and the y's are. And I'm going to work through it, and I'm going to try to get the y by itself. Now you can think of a whole bunch of different ways to do this. What you're going to notice here is that it's really, really hard to do unless you have memorized completing the square. And I want to talk about why this is real quick. Our last little note over here says that f is invertible if, with two f's, which is like saying if and only if, it passes our horizontal line test. And that's kind of a loose definition for function invertibility. But for the purposes of college algebra, if it passes the horizontal line test, then you have an injective function, which means you can find an inverse for it. What you'll notice about this, let me show you a graph. X squared plus 5x plus 6 kind of looks like this, more or less. It actually does cross the x-axis in two places, and I should probably do a little bit better job of showing that. So it kind of looks like this. Now, think about what the inverse function does. The inverse function is supposed to swap the range and the domain so that the outputs, the vertical part, become the inputs, which means I'm going to map these to the horizontal line, and the inputs, which was originally the horizontal line, get mapped to the outputs. The domain becomes the range. So what was going horizontal now has to go up and down, and what was going up and down now has to go horizontal. Long and the short of it can be kind of hard to visualize without somebody just spelling it out for you. We effectively need to reflect this parabola across the line y equals to x. Now think about why that is. Up here, I switched the location of the x's and the y's. In other words, I said, well, y is equal to x, and x is equal to y, which is exactly what that expression says right there. And then if I solve this out, what I'm going to get is an inverse function of some description. So now I'm going to do my best to flip this thing over. It's kind of hard to do. I think this is how it works. If I flip this thing over, I get this kind of parabola. But you'll immediately notice a problem with this, because one of the things that we established in the early going about functions, and that you were required to recite over and over and over again on the homeworks, is that a function is only a function if it passes the vertical line test, because there can't be ambiguity as to what the output is. Notice that this does not pass the vertical line test. And what that means, essentially, is that something like this that doesn't pass the horizontal line test doesn't have an inverse, or at least not an inverse over its entire domain. So we have to put these funny domain restrictions on it. In other words, we're going to lose some information about the original function when we find the inverse. But notice that if I erase this part right here, this lower part, then I don't have a problem. I've got a nice function right there. And we've already kind of talked about how that was when we talked about the parent functions. Remember that the squaring function, in other words, x squared, a parabola, had its inverse parent function, which was the square root function. It looks like this. That's kind of where that's coming from. Okay, so actually going through the motions of solving this thing, really, really hard. In general, what you want to do is you want to isolate the y. So I'm going to do that with the completing the square portion of this. Okay, so I have x is equal to y squared plus 5y plus 6. And I'm going to write the plus 6 kind of out here to the side because I need to complete the square in order for this thing to work. So completing the square, if you remember, what we do is we put the constant out to the side. If we have a leading coefficient here, we need to divide it through everything to make sure that it is a 1 before we start this procedure, otherwise it doesn't work. And so what I need to do is take half of this middle number here. So half of 5 is 5 halves, and then I need to square that result, which is going to be 25 fourths. So just square the top and square the bottom. And I need to both add that 25 fourths and subtract that 25 fourths. Now we might want to go ahead and put 6 into fourths just to like make this fraction business a little bit easier. 6 is 24 divided by 4, so it's 24 fourths. And then remember what the point of doing this is that if I consider the quadratic portion right here, kind of ignoring those extra constants out to the side, the minus 25 fourths is just to make sure that I'm basically adding 0, and the plus 24 fourths is just like the constant on the outside of the vertex form. This will have the effect of putting it into the vertex form, where all I have to do is take a square root of the first term, the ax squared term in the quadratic, and then I need to take the square root of the c term, which of course we know is already 5 halves. We steal the sign out in the middle, and then we square it. It makes a nice perfect square trinomial. In other words, when I FOIL out y plus 5 halves squared, I'm going to get y squared plus 5y plus 25 fourths, exactly what I have there. But I have these extra constants on the outside. Minus 25 fourths plus 25 fourths is minus 1 fourth in total. And that is equal to x. And now notice that, first of all, if I had completed the square back here, then I could just do common sense things to find the inverse in the first place because there's just one variable. But I do want to show you, if you switch the location of the x's and the y's, maybe there's some processing that has to happen, but we still just want to get the y by itself, and that is our inverse function. So if you think about it, if I add a fourth, I will get this expression. If I square root both sides, that will have the effect of canceling the y plus 5 halves squared portion, the squared portion of that, and just leaving me with y plus 5 halves. And then if I subtract 5 halves, I get y by itself, which is my inverse function. Okay. So there's kind of a lot of examples of how this gets used. I'm going to show you one more that maybe will work a little bit better. In general, whenever you have multiple x's, you're going to have to do this business of switching the x with, change the x to a y, change the y to an x. Or anytime you have an x in the denominator. I'm going to show you how that one works right now. Okay, so I'm back. I've cleaned up the board. I've put a rational example up here. Now this one is particularly interesting because I've got a rational function. I do want to show you first of all that we're not going to have any like crazy funny business like we did in example 3. So I want to do the whole thing. I want to test to see first of all, is it invertible? Because as you see, example 3 was kind of precarious, and that's because we didn't test before we began with it. And that's because I wanted you to kind of run into that problem on your own so that you can kind of rationalize where is that coming from and why might that happen. So if you were to graph this thing, what you would get would be a vertical asymptote at x equal to 2 And then for all the numbers that are to the left of 2, we would get this kind of negative looking thing, and then for all the numbers to the right of 2, we would get this positive looking thing. It looks like that. Now you might notice that I could take kind of any number of horizontal lines across this thing, like one there, one there, one there. I do have a horizontal asymptote here, so that doesn't really matter all that much. But notice that no matter what horizontal line I draw across this thing, I only ever touch my pink graph in one place. And that's really important because that's kind of the same thing we did in the vertical line test. The difference is that the horizontal line test means that this thing has an inverse. And since it has an inverse, that process that we're going through isn't going to require any special finagling or constraints on the domain. So I'm going to show you how that works at this point. So first thing I want to do to find an inverse is take the f of x and replace it with a y. So that I have y equals 3 over x minus 2. Then I'm going to literally switch all of the x's to y's and all of the y's to x's. So you see a y, write an x. You see an x, write a y. Now what I want to do is I just want to solve for y. Okay, so think about this. When you see fractions, we want to clear the fraction by multiplying everything by the denominator. So if I take this whole expression and multiply by y minus 2, that will give me x times y minus 2 on the left-hand side. On the right-hand side, the denominators match, so they cancel, leaving me with a 3. Okay, but I want the y by itself, and I just created a problem because x and y are together. Let me divide both sides by x, which gives me the right-hand side, 3 over x. The x's will cancel off of the left-hand side, leaving me y minus 2. Then, of course, the next step should be pretty obvious. I'm just going to add 2 to both sides. I'll have 3 over x plus 2, and that is my inverse function. And you got to be kind of careful on these because you'll notice that this is one variable, and I didn't even attempt to talk you through like the quote-unquote common sense way to do it. And that's because the common sense way has some serious limitations, and that is that things like this are really, really hard to talk about. So if you get into something and you're like trying the common sense way and you're having to do weird things to describe what the last thing that you did was, go ahead and try putting the y's as the x's and then solving for y to get your inverse function. Okay. Now, last little thing, remember, big takeaways. An inverse function just flip-flops the inputs and the outputs, so it takes an output and it returns the original input that made it. It just undoes everything that a function did. If x and y is a point on the original function, then y comma x is a point on the inverse function. Furthermore, we know that not all functions have true inverses, and I'm going to say the word true because you may want to Google this a little bit later. Not all functions have true inverses. So the way that we can tell which ones do have true inverses is by testing them with the horizontal line test to see which ones are invertible. And that is, if I do the same thing that I did with the vertical line test, but I do it with a series of horizontal lines, it will tell me whether or not a function has an inverse without messing with its domain. Okay, if you can do these things, you've got section 4.1.